Today, I want to start in on the substantive issues, the economics of discrete choice. So we'll start out describing discrete choice models in general, and then turn to a specific discrete choice model called Logit, which is by far the most popular, most widely used model. And then end up the day talking about a computer workshop that we'll be doing, describing the data and what the exercises are. Before we get going, though, how many of you have actually estimated a Logit model in your past? Yes. So these are widely used models. Glad to see people have been working with them. They're important to understand because they become the basis of a lot more sophisticated models or more general models later. Anyway, so let's start with just discrete choice in general. The economic situation that's being described is that an agent, a decision maker, has a choice among several possible actions. We label them by index J up to capital J. So there's a capital J number of alternatives available. Obviously, different agents could face different numbers of alternatives. So in a sense, you could subscript this J, capital J, with a little n for the alternatives available to that person. For example, if you're going to work, some people don't have a car, don't own a car, and so that option's not available to them, or they're not capable of driving, don't have a license. So that alternative might not be available. The set of alternatives has some characteristics that need to be met for a discrete choice model to be applicable. First of all, the alternatives are mutually exclusive, which means that if a person chooses one alternative, they don't also choose another alternative. Okay? Choosing one means you don't choose the other ones. What's an example where that would not apply?
Credit cards.
Credit cards, right. You can choose to have several credit cards, so if you choose the AT&T credit card, doesn't mean you're not choosing the Mileage Plus credit card or whatever the other one was. Another example would be if you're choosing how to get to work and your options are car, bus, or rail, you can take the bus to BART and then BART, and so those are two that you're taking. In those situations, usually you want to redefine your options such that they're mutually exclusive. For example, you could have the modes to work being car, bus alone, BART alone, bus with BART, or you could define it as the primary mode. So then it would just be car, bus, or BART, and you make a decision as a researcher on what's the primary mode. But in any case, they need to be mutually exclusive. Secondly, the alternatives have to be exclusive. The set has to include all the possible options, so the person necessarily chooses one of them. And then finally, the set needs to be finite. You need to be able, as a researcher, to count the options and eventually quit counting. Then, given those, the economic theory of the decision making is very simple. Each person gets some utility from each option. So N denotes the agent who's making the decision. I is the alternative. The person chooses the alternative that gives them the highest option. So N chooses I if and only if utility of that alternative is greater than utility for all the other alternatives. And that's the decision process for the decision maker. It's very simple. Now, as a researcher, we would like to understand what the utility is that affects this person. We recognize, however, that we have limitations on how much we can actually observe. So we decompose this utility into two parts. A part that we can observe as researchers. It's based on variables that we can observe, measure, put into a model. And then there's necessarily factors that we can't observe, and we label those as epsilon. This is following the lecture from last time in that there's some things that we can observe and some things that we can't observe. The things we can't observe we treat as random. If we could observe everything, then we could perfectly identify what the utility of each option is for the people, each person, and then identify which one's highest and perfectly predict what that person's going to do. We can't, and so instead we use the information we've got to make good guesses, probability statements about what the option would be. So we have a separate unobserved factor for each alternative. Let's collect those together into a vector. This is the errors or unobserved factors relating to person N. There's one of these for each alternative. Okay. And then with that, we can easily calculate the probability of the person making a particular choice. So the probability of their choosing alternative I is simply the probability that the utility of that option is greater than the utility for any other option. Okay. Substituting in and then rearranging terms into a way that makes it easier for us to look at. I'm going to switch to blue because that black marker seems to be giving out. We want to have this be a cumulative distribution. We can do that by taking this one over here, the error term over there, and this observed thing over here, and then it becomes something greater than an error, or rearranging it to be the opposite direction. This is a cumulative probability. This is the cumulative probability that this error difference, which is a random term, each element is random, so the difference is random, is less than this observed quantity. I want to talk more exactly what that is because the meaning of these probabilities is extremely important. But then to put this back into the form that we were describing last lecture, you can state this instead as the integral over all values of the unobserved factors of an indicator variable that the event, how am I doing this? Yeah. That event occurs for all j not equal to I, okay, times the distribution of this error term integrated over all possible values. So this probability, if we know the distribution of the error terms, can be explicitly represented as this integral. It's just on an average of this indicator variable over all possible values of that unobserved factors given their density. Obviously, you will get different expressions for this integral depending on the distribution of the error terms. And different discrete choice models simply arise through different definitions of the density for the unobserved factors. Logit has a very simple distribution. It assumes independence across the alternatives and homoscedasticity. And then the whole course of the field has been moving towards more and more flexible densities for these error terms. But let me talk more about what exactly this probability means. So when you're working on the economics of this, when you're doing your own model, you really need to think about how to consider these probabilities. So let's have a problem where we've got a car versus bus as the two alternatives. The utility of car is equal to an observed part that we can see and an unobserved part, and similarly for bus. And let's suppose that based on what we can see, car looks better. So we can consider the cost of driving by car and the time of going by car and compare that to the cost and time of bus. We know the person's value of each of those things. We've estimated it perhaps as parameters. And we evaluate that car is better than bus by 1 util. Okay? What does that mean? Well, the incorrect thing to say is that that means the person's going to choose the car because it gives them higher utility. It only gives them higher utility on the things we as the researchers can observe. Okay? What is the probability that they're going to choose a car? Well, let's think about the things that we don't observe. There's a lot of things about cars and buses that we don't observe. Some people like to be in their car because they can listen to the radio and not have to interact with people around them. Some people like to be on buses because they have the possibility of meeting someone for a date, or sparking, or they can read, if they can sit down. So there's possibilities of, there's people that like each of these, and we as a researcher really don't know for any one person which category they fit into or how they evaluate these. So the person's going to choose a car in this situation unless the unobserved factors are so much better for bus than car that it overrides the observed factors. Essentially, since the observed factors are better for car, they're going to choose a car unless the unobserved factors are so much better for bus that bus ends up better altogether. That's essentially saying that probability of getting a car is the probability that when we look at bus unobserved factors compared to car unobserved factors, the person will continue to buy a car as long as bus on unobserved factors doesn't dominate by at least the amount that car dominates on the observed factors. And that's essentially what this is saying. Okay? Huh? This is the probability. Right. So all this probability statement is saying is that we observe what's best and how good each alternative is on the observed factors. The person will make choices in accordance with that unless the unobserved factors reverse what's best. Essentially, this is saying the person will choose car as long as this is not greater than 1. If it is greater than 1, bus is better than car on unobserved factors by more than 1 util, then they'll go ahead and get a bus. Probability is the bus is the probability in this 2-dimensional case that this overrides. Okay. Now, given this, that what we're actually doing is trying to determine which alternative is best on observed and unobserved factors. There are a couple of characteristics of choice models that always occur and need to be taken into account when you're doing your estimation. In some situations, like logit models, these factors are taken into account kind of automatically for you. In a sense, the distributional assumption already factors into these issues. But when you get into other models, like Probit particularly, or mixed logit, they won't be, and you have to impose them and recognize these issues on your own and make sure you don't violate the concept. First one is only differences in utility matter. Maybe this is cooked up again. What this is saying is if you have alternatives, say 1 and 2, you can add a constant to both of them and it won't change anything. It's irrelevant. You just add a constant. Whichever alternative was highest to start with is going to be higher with that constant added. Another way to look at that is that it's only the differences that matter because the absolute level is irrelevant. You can think of this very visually as a rising tide raises all boats. You're looking at a harbor, the tide comes in and all the boats go up and down. Whichever boat was sticking up the highest to start with is going to be sticking up the highest even after the tides come in or gone out. Okay, so a constant added to all the alternatives changes their levels but does not change behavior. It's irrelevant to the behavior. It's irrelevant to us as the researcher. And if you try to estimate, it's unidentified. If you tried to add a constant to each alternative, it's unidentified. Another way to look at that is in this probability statement, it's only differences in representative or in observed utility and unobserved utility that matter. If you added a constant to each of these terms, it'd drop out. Add a constant to both of those, it'd drop out. This has a couple of implications when you're estimating. First of all, if you're adding a constant to each alternative, you could think of a model in which a person has a constant, instead of adding k to each one, add like k to this one and g to that one. So it's a different amount added to each one. It's not the same constant, so you're raising them by different amounts. This model is absolutely equivalent to adding the difference in those two constants to one of the alternatives, okay? Because only differences matter. If you tried to estimate your model with a constant in each of the alternatives and tried to estimate a separate constant for the two, you'd get, your model would blow up, you wouldn't get convergence, because it's not identified. Essentially, the levels of the constants are not identified, only the differences. And so one thing you have to do if you're adding constants to the model, one constant to each alternative, is to normalize one of them to be 0, and all the rest of them are then interpreted as being relative to that one. Essentially, this is saying we can't know the level of happiness that's associated with anything. We can only know relative happiness. And these constants capture. It's important, putting these constants in is useful, as you'll see in the workshop, because they capture the impact of all things that are not explicitly included in your variables. So they capture, in a sense, the average impact of everything that's left out of the model. They also, by putting them in, force these to have 0 means. Essentially, the means get picked up in these constants. So it's good to put them in, but you need to remember to put them in only to all the alternatives except one, and then they're all interpreted as against that. Similarly, if you're putting in socio-demographic variables, for example, you think people are happier when they have higher income. So one way to think about that would be to say, okay, well, let's add income to each alternative. Okay. It's probably true that people are happier, with higher income, no matter what mode of work they travel by or whatever other options they're choosing. But if you try to add for each alternative with the same constant, with the same coefficient, then it's going to drop out. It's essentially the same as if you didn't have it. You could have a separate coefficient for each one. You could say, well, income affects your utility differently depending on which alternative you happen to choose. That would make sense. Okay, so we're adding a different amount. Okay, so it's not just adding the same amount and hence it drops out. But then that would be, you couldn't estimate the levels of these. You could only estimate their difference. So the procedure would be to set one of them equal to 0, one of the coefficients equal to 0, and estimate the coefficient that enters the other alternative, and interpret that as the impact of income on alternative 2 relative to alternative 1. So again, since only differences matter, you can't estimate the level of the impact of an added socio-demographic term on each alternative. You can only estimate the difference. Do you need to change videos? This fact that only differences matter affects how you enter your variables and how you interpret them. It also has an impact when we get to simulation on what dimension this integral has. As I've written it here, it looks like we're integrating over j dimensions of an error term. But as you'll see, only differences matter. We're taking each of the non-I alternatives and subtracting out the ith. Okay? So essentially we have j minus 1 error differences. And so this integral can be expressed as j minus 1 dimensional rather than j dimension. And that saves you one dimension of simulation. if you want to use it that way. A lot of times you want to go with the j-dimensional integral instead of j minus 1 for pragmatic reasons or whatever, but you can reduce it to j minus 1. That saves one dimension of integration. Second thing is scale of utility is irrelevant. If in is greater than ujn, then that's also true even if you multiply them both by some constant. So whichever is the highest alternative, it's going to be the highest alternative, highest utility, however you measure the units. This is essentially saying that if you measure utils, whatever units you measure utils in, it doesn't matter. If you're looking at profits here, the same is true. It's not just that utility is unmeasurable that this is the result of. If you're measuring profits in dollars, hundreds of thousands of dollars, pennies, it doesn't matter. Whichever option gives you the highest profit, you're still making the most. So it's not, neither of these is a result of utility being a concept that can be scaled arbitrarily. It really has to do with just maximizing concepts. What this means is that you need to set the scale of the model in some normalizing fashion, that the scale cannot be identified. It has no meaning. Okay? So usually the way to do it is by setting the variance of the error term. You don't have to do it this way, and we'll see when we get into probit models that there's other ways to do this. But one way to do it is to set the variance. If you start out with a model or thinking in terms of a model where this is equal to, say, sigma squared times k, the variance of this error term, you could redescribe your model as being now the variance of your new term, so you're just dividing through by sigma. The variance of your new error term is equal to k. That's good because essentially you can choose k such that this error term is a standardized form, such as if you want this to be a standard normal, you can say, okay, well, I want my k to be 1. That gives this a standard normal. That's equivalent to dividing everything in the model by the original standard deviation of your error term. It's a way of setting the scale of the thing. You can set the scale by setting the variance of the error term. What this tells you then, and this is important when you're interpreting, that all the variables or all the parameters that are entering the observed portion of utility are scaled by the variance of your error term, the standard deviation of your error term, if that's the way you're doing your normalization. And this has an interpretation. So for example, suppose you have the observed portion of utility is linear in parameters. So you've got variables like the cost and time of an alternative, and then you've got the coefficients of that. And you're interested in one coefficient. You need to remember that this is implicitly the same as estimating what you're actually doing is you're estimating the value, the coefficient of the variable itself divided by the standard deviation of error term. That's what's setting the scale. Okay. So when you're estimating the estimated parameters you get back, incorporate two things. They incorporate how important is that variable and how large is the variance for the error term in some abstract sense, unscaled sense. And an example would be car versus bus, whether to travel. Let's say this is time for bus. And this is the probability of bus. You could get estimates that if your estimated beta is high, then what you get is a function that looks like this. Essentially, in a two alternative situation where you've got only car and bus, if the time on bus is lower than the time by car, and time is extremely important to people, then they'll choose the bus because it's quicker. So in the range where the time for bus is below time for car, the people will nearly always choose the bus. And then if the time for bus gets greater than the time for car, so it takes longer to go by bus, since time is very important, they will switch over and take a car and not take the bus. So when you get a high beta, what that means is that you get a very precipitous drop at a cutoff point where that alternative starts to become the best. Alternatively, if you have something like this, that results from a lower estimated beta. What that means is even if bus is quicker than car, there's other factors that are going to cause the person not necessarily to choose the bus. They wouldn't necessarily choose the bus because of these other factors that are going in. Now, what's interesting here is this difference in whether you've got a high beta or a low beta do not simply denote how important time is. In a sense, how important time is a meaningless concept. It's how important time is relative to something. And since it's scaled by the variance of the unobserved factors, it's telling you how important is it relative to all that stuff you've left out of the model. Here, when you've got a high beta, that means sigma is low, the ratio is high, okay? Meaning that these other factors really don't affect utility much. There's not a lot of variance in these other factors, and you're really dominated by what you observe as a researcher. The decision is really dominated by what's observed, in this case time. And so we can observe that the person's choosing the thing that's best on the observed factors, and that gives us this really precipitous drop. On the other hand, if there's all these other factors out there that have a lot of impact on people's decisions, the error term is going to have a large variance over people because there's these factors that are random, that affect their decisions that you don't observe. They create a lot of noise in the decision process that you can observe. And the things you do observe don't matter so much, so you get a curve that's more like this. So it's really important to recognize that the value of these parameters, the absolute value that you get in your estimation, depends not just on how important that factor is that you put into the model, but how important it is relative to everything that's been left out. That's essentially what it's telling you. That's another way of representing the concept that scale is irrelevant. Yeah?
Betas at the top, what's that star?
I'm sorry?
The equation at the top, looks like one of those should have a star.
Why should it have a star?
Because you divide it by sigma on the right.
Oh, I see. Yes. You could put a star here. It's, huh? In the V? You could express V as either this or this, where B star over sigma is equal to beta. Beta star over sigma is equal to beta. Yeah, that's a more precise way to do it. Okay, so each of these things has to do with how you specify your model and how you interpret the model. That's important. Okay. Now, the last thing I want to talk about general choice models is how to do forecasting and aggregation. The important thing to recognize is that a discrete choice model gives a nonlinear response, as I've described, kind of drawn here, and we'll see in specific models later what exactly the response surface looks like. But in general, it's not linear. And as a result, forecasting and aggregation is distinctly different than what you'd have in a regression model. In particular, you cannot, if you're forecasting for a group of, or calculating the average probability over a group of people, and let's say this is your explanatory variables x, this is the probability of a particular alternative, and let's say it goes like this, from 0 to 1. If you have a set of people in the population and want to estimate the average probability for them, you cannot simply stick in the average of the explanatory variables and get the right answer. If you were, say, two people, one of them faces attributes XA, another one faces attributes XB, this person's probability is here, that person's probability is there. The average of those two is the midpoint of this ray between them. Okay? So this is the average probability for those two. If you were to actually take the average of the explanatory variables, it would be the midpoint here, xa plus xb divided by 2. And sticking that into the formula, the choice probability formula, you'd get that value. And so you'd be off by the difference. This is extremely important. It differs from regression. With regression, if you have x and y in linear regression, the average of y for the two observations is going to be the midpoint between them. If you were to take the average of the explanatory variable, sticking it into the model, then you'd get exactly the same answer. So because of the linearity, you don't have to worry about this with regression models. But with nonlinear models, you have to worry about it. The way to get the average probability is through what's called sample enumeration. You explicitly calculate the probability for each person in your sample. So the average probability for alternative I is equal to the probability for each individual person in your sample divided by the sample size. Okay? So you have to actually do it for the entire sample. That's what's called a sample enumeration. Calculate the probability for each person and in the sample, add it up, take the average, and that gives you this correct average probability. When you're forecasting, this average probability is your forecast of the share of the population that will choose that alternative. So in forecasting, you can use this average probability as a prediction of the share of people in the population from which your sample was drawn, that would choose that alternative. This is extremely important also when you're looking at changes. It's even more important, in fact, when you're looking at changes. And usually you're not interested in shares per se. You're interested in change in shares as a result of some policy that you might be implementing. So if we have x and pi, you could have like two people. Say xa is here, xb is here. Each of them, if you change the explanatory variables, give a rebate to the alternative so that it's cheaper or whatever you're going to do. Neither of these people responds much, so the response curve has a very shallow slope for each of the people in your sample, and yet and that means the average response is going to be low, so the predicted impact of this policy is low. And yet, if you went in and tried to do it at the average of these two, you're going to end up in the very steep part of the curve and think that the policy has a big impact. So again, you do sample enumeration to get the impacts. The easiest way to do it is to predict the average probability before the change and the average probability after the change, and just compare the two. You could actually use formulas for the derivatives and then take the average derivative, but I found that usually is harder. Okay, now, what I've said so far is true of all discrete choice models. What I now want to turn to is what is a logit model and what are the special properties of logit models. Start with a regular derivation. Utility is broken into an observed part and an unobserved part. And now what we're going to say is that there's a particular distribution on this unobserved part, and that gives us a discrete choice model of a particular form. For logit, we assume that each of these is distributed independently, identically extreme value. Okay. That means is the density of each one is equal to e raised to the epsilon, negative epsilon, e. Okay, so that's the density. Why that density? Because if you work through the the probabilities and actually explicitly do the integration, then you get a choice probability that looks like this. This is an extremely easy choice probability to work with. So if you want to see this derivation, it's in the last section of the chapter in my book on logit models. There's no economic intuition behind it. It's simply manipulating this density, integrating over the indicator function that I'd given earlier, and you'll end up with this being the explicit integral. So now, that clearly is the reason this distribution was chosen. The reason this is chosen is because it gives us a nice, easy form, an analytically integratable form for that, that expression, that choice probability. And this was the essence, as I kind of explained last lecture, of doing discrete choice modeling and most all of econometrics up until simulation, in that the trick was to find distributions and behavioral models which, when combined together, would give you an integral that you could actually integrate analytically. Okay, and this is just an example of it. What does this distribution look like? It looks very much like a normal when you look at the differences in error terms for alternatives, and all that matters is differences. It essentially looks like a normal distribution. It's got fatter tails, and this standardized form has a variance of pi squared over 6. So when you're comparing a logit with a probit, you have to recognize that this is scaled to have a variance of pi squared over 6, whereas a probit with independent error terms, standardized, will have a variance of 1. So there you have a different variance, and as a result, all your coefficients are going to be scaled differently. So if you get different coefficients in the two, that doesn't mean you got fundamentally different economics going on. You have to make sure to rescale one to match the levels of the other using that. Okay. But otherwise, it essentially like a normal distribution, but unlike a normal, it gives you an explicit formula for the choice probability. As you can see, this probability goes between 0 and 1. It can never be outside of that range. If this were negative infinity, the top becomes 0 divided by something, and that's 0. If this becomes positive infinity and everything else is fixed, so the observed utility of one alternative rises without bound while the other ones remain fixed, then this simply becomes a very large term in the numerator, a fixed amount plus a very large term in the denominator. Those two cancel out, or those two dominate, and it becomes 1. Okay. So this goes between 0 and 1. Also, the denominator is simply the sum of the numerator over all the alternatives that are available. And so if you add up the probabilities over alternatives, it adds up to 1. That's important. The probability of doing something is equal to 1. That means the person chooses one alternative and only one alternative out of the set. The last property that I wanted to talk about with it is that this formula gives you a nice sigmoid shape for the probabilities in each of the variables. This has policy implications of its own. You can have choice models that don't have a nice sigmoid shape like this if you believe that your choice situation should be represented differently. But with this, it's an interesting policy implications here. What this tells you is that if this alternative is extremely good to start with, it's got a very low cost perhaps, okay, then improving it doesn't really help much. Similarly, if this alternative is really lousy, it's got a really high cost, hardly anyone buys it, improving it won't help much. Where you really get the action is right in the middle, where the probability is close to a half, where essentially a probability of half means that on the basis of this attribute, it's pretty much a coin toss whether the person will take this alternative or not. That's where improving it does a lot of good. Improving this alternative then can kick the person up quite a bit. This is important, for example, with transit planning. There's no point putting in transit where essentially improving transit when that's by far the best mode anyway. In like Manhattan, there's some places where it's practically impossible to drive, but you can easily get there on transit. So improving transit in those situations really won't help things much if your goal is to increase transit ridership. Similarly, if transit's really lousy, like going from Novato to San Francisco on transit compared to a car is really lousy, improving that doesn't help much. Where you really want to do things is where you're at that cut point. Transit agencies really, a lot of businesses in fact, think that they should be working where their service is extremely poor. And that's not true. You're really not going to get much bang for your buck where you're trying to improve an alternative that's not too good to start with. You should work where it's kind of like right on the cusp, the trade-off. Okay, estimation of this model is done in exactly the same way that you did at 240 A and B, maximum likelihood estimation, because you've got an explicit closed form for the probability. So we've got the log likelihood function is the sum over n of a dummy variable that identifies what that person did. So d sub I n is equal to 1 if person n chose alternative I and 0 otherwise, okay, times the natural log of this probability. Okay. So we get a log likelihood function that depends on the underlying parameters that enter V. It's just exactly the same that you've dealt with before. I want to draw a picture of it because we're going to be looking at this later. One way you can think about this is a parameter. This is the log likelihood evaluated at that parameter. You get some surface, and the maximum likelihood estimator is the top of that likelihood function. You can verify on your own that with the logit model, this will be one-humped. You've got a concave function, globally concave, which is another great thing about logit models. If you're using maximum numerical routines for maximum likelihood, then you will get to the top easily, and you won't be confused with a local maximum versus a global maximum. So things work out extremely well. Why did I write this going down this way? This is 0. This is important when you're estimating your model. I have to think about it every single time I sit down after 25 years doing this. The log likelihood is always negative because the best you can do is get a probability of 1. The log of 1 is 0. The log of anything lower than 1 is negative. So the log likelihood is always negative. So maximizing the log likelihood means minimizing its magnitude. So it's important. Often you'll get a log likelihood of 7783 and 7762 or 0, and that one looks bigger, that one looks better, but you got to remember it's not because they're both negative. Okay, then with discrete choice models, there is a goodness of fit statistic that is useful to use to measure how well you're matching the data. Yeah.
So should that be a double summation over n and over I?
Right. Exactly. Because essentially this kicks out all the alternatives that aren't chosen, so it's that way. It's called a likelihood ratio index, often called rho, though I don't know why. Rho is often used for serial correlation, and I like keeping it for that, but it's used here too. It's defined as 1 minus, got to get this right, the log likelihood at the estimated values divided by the log likelihood at 0. Okay? You can rewrite that as log likelihood at 0 minus log likelihood at your estimated values divided by the log likelihood at 0. Okay? And you can think of it visually. It's this distance is the denominator. What is the log likelihood when your coefficients are set to 0 compared to that distance, which is the difference between the log likelihood at 0 and the log likelihood at your converged values. This has an intuitive meaning. If you could get a perfect model, the log likelihood at convergence would be equal to 0. Log likelihood of 1, or the log of 1 is 0. So a perfect model would bring this hump up to the axis, the x-axis, and touch 0. So in a sense, what this is telling you, this distance here, is how far is your model, how to put this. This is the distance that you'd need to go to get a perfect model. This is the distance that you're actually going in your model, going to the converged estimated values. And so what this log likelihood statistic is telling you is what % of perfection are you attaining with this model. It's the amount that you're improving the model compared to the total potential improvement that's out there. Okay. So you can kind of think about it that way. If you get a 0.23, that means you've gone 23% of the way to perfection, and you got another 70, whatever it is, 77 left that you could, if you had enough explanatory variables and understood the process well enough, attain. The log likelihood at 0, you need to recognize, is a model which is essentially a model of chance. That says that we don't know anything. All the coefficients enter as 0, and this is essentially the same as flipping coin. If you've got 6 alternatives, the probability is 1/6 for each one, and so this is the log of 1/6 added up over all people. So this is the purely chance model. This is a perfect model, and this is the model that you've got. Yeah.
Does that assume even there's no constant for each?
Aha. There is a difference of usage on this. Some people calculate this with all coefficients, including the constants, set at 0 for log likelihood at 0. Other people calculate it where everything except the constants. So essentially the constants are in there because they simply reproduce shares. And so you're kind of allowed to use those because that's essentially saying, well, it's chance, but we know the shares, but nothing else. We have no causation, we just know aggregate shares. And then you calculate against that. You can do it either way. It depends on which one you find more satisfying. What's important, though, is when you're using a computer program to know which one they're using, because they very seldom will tell you. They just say likelihood ratio index. SST does it against 0, including the constants being 0. Anything else? Yeah.
DIN in the log likelihood.
Is that what?
Yeah, what is that?
This identifies the chosen alternative. It's 1 if person N chose alternative I, 0 otherwise. So you can think of this as the dependent variable. This is the log of the probability for each alternative. Yeah?
So if you program this in normal situations with as many coefficients as you want, there should never be a number of local maxima. It'll show it clear what the maximum is.
As long as V is linear in parameters, and you're in a logit formula, there'll be a global maximum. There's just one maximum, and it's global. There are ways you could get the if you have nonlinear in parameters. There are ways you could specify that nonlinearity to create multiple maxima. But as long as you stay linear in parameters, linear in parameters is very flexible because you know you can approximate any function with something that's linear in parameters with enough pieces. So there's really not a restriction there. Okay, how does this compare to R squared? There's essentially no relationship between R squared and this, even though each of them goes between 0 and 1, and there's a tendency to want to think of this as an R squared. It really has no relation. R squared gives you the % variation in the dependent variable that is explained by the explanatory variables. I mean, that kind of sounds intuitively like what we're doing here, but it's not. So you shouldn't try to make that comparison. Also, generally you'll get these values around 0.1, 0.2 with cross-sectional data. And you might think that's lousy because in regressions, you know, especially when you use time series data, you'll get them up 0.98, 0.99. That's really a difference in two things. One, in regression with time series data, usually you get a really good fit for each observation just by looking at the previous observation. And so, you know, those high R squareds are a little bit deceiving in the sense of what you're actually learning from the situation. With cross-sectional data, even with regressions, you don't get high R squareds like 0.98, 0.99. There you get them, you know, closer to what they are here. But the other thing is that they're just not the same number. Okay, so you need to keep that in mind. Then finally, there is a testing procedure that can be used, which is similar to what you've done in a maximum likelihood before. Just want to repeat it. You can always use t-statistics on your individual coefficients. If you're wanting to test something more than that, though, you can use a wall test like you've learned. I find that difficult. I find it hard extracting the parts of the covariance matrix that I need. It's just tedious keeping up with which row and which column you want to extract. It's easier to use, I think, the likelihood ratio test. Okay, so a hypothesis that you're going to test is always some kind of restriction on your model. Okay? And the likelihood ratio test calculates a statistic which is 2 times the log likelihood unrestricted minus log likelihood restricted. Or since I am always forgetting which direction the negative comes in, it's better to look at it that way. It's the difference between the unrestricted and the restricted log likelihood times 2. This is distributed chi-squared with degrees of freedom equal to the number of restrictions.
To get the positive number is minus, right? You put the absolute value.
I put the absolute value here, so you always end up with a positive number. This one's, anyway. So, for example, if you want to test the hypothesis that two coefficients are equal to each other, you estimate the model once when they're not equal to each other. That gives you the log likelihood unrestricted. You estimate it a second time with them restricted to be equal to each other. That gives you that. You find how much the log likelihood changed, multiply it by 2, and that gives you a chi-squared statistic. Suppose you end up with log likelihood restricted is equal to negative 0.738.2. Log likelihood unrestricted is negative. It's going to be a smaller number. Okay. This is where the negatives always screw you up. The unrestricted is a smaller absolute number. So then taking the difference between those is 3.2, multiplying it by 2, 6.4. If this is one restriction, you're testing two coefficients and whether they're equal to each other. That's one restriction. That's a chi-squared with 1 degree of freedom. What's the critical value of that at 95% confidence? Does anyone remember? It's right around 3.8 at 95% confidence. So with this test, you would reject the hypothesis that the two are equal. This is a test that you can nearly always apply. It's very rare that you would come up with a hypothesis that you can't do with this. It requires running the model twice. You have to think about what would be the unrestricted model, what's the restricted model, and run it both times. But as you'll see with logit models, you can run them in a blink of an eye. It's easier to run a model than to think about how to deal with a covariance matrix of parameters. You just do it. When you get into the other models that are harder to estimate, then you have a trade-off between doing